is 100, you will have axial loading from the 100. And the 25, so if we were to draw a transformation, so before I go on, I need to draw a transformation. So what do I mean by transformation? So you have to tell the general audience that which is your X. Okay, so this is our X direction. Sorry, that's our Y. Okay. Now, by the way, every mistake that you spot on my lecture, stop me. Okay. And I'll buy you beer when the bloody virus is over. Okay, I'll buy you beer. Okay. So this direction, so this is our X, and this is our Y, and then based on right hand rule, that is our Z direction. So this is our Z direction. So from here, you can see that the 100 will cause a axial load, okay, and then is also going to cause a moment in the X direction, okay, moment in X direction, and then you will also look. So that is from the 100. Now the next one we're going to look at is the both 8 kilonewtons. So these both 8 kilonewtons will generate a shear force, okay, the shear force V in the X direction, and it's also going to generate a moment in your Y direction, okay. And then the 25, as you can see, as you can see over here, I'm going to use a different color. So the 25, you can see over here, will generate a shear force in a Y direction and a moment. It will generate a moment in the X direction. Let me see. Yeah, it's a moment in the X direction. Now, don't worry how to identify this yet. Okay, as I said, this you will be able to identify all this loading probably on week 5 or week 6. Okay, I'm just giving you a taste, a preview of what's going to happen in this course. Okay, so just stay back, relax. Okay, but don't sleep. Okay, I will ask random question. Okay, right. So the next thing is, as I said, what is the purpose of this course? Right, I think the big objective is once you get a structure like this, how to choose the right material as engineers. Okay, as engineers, we have to be very critical on how we choose the right material. Okay, I mean, without this information, you choose the most expensive one. Okay, you choose the beam that's the biggest. Okay, but if you have things that are flying around, you can't do that. Okay, it has to reduce weight, or if you have to reduce cost, you cannot always choose the most expensive stuff. You have to optimize. Okay, that's what engineers are all about. You have to optimize. Now, why principal stress is required? Okay, so if you look at material properties, okay, if you look at material properties, from any handbook, from any material handbook, okay, if you look at any material properties from, so if we go back to fundamentals again, we look at our stress strain curve, right? So this is our strain, this is our stress, then we have a linear relationship, we do a drop, and then we go here. So we carry out tests. Okay, so experimental work or tests or experimental tests. are acquired or are required to find the relationship between stress and strain, like what you see over here. And as I mean, this chart, all of you should be very familiar with. If not, I can do a very quick recap. So if I draw a line here, so over here, this is our elastic region. On the right hand side is our plastic region. So for this course, okay, so MECHENG 2PO4, you want to be in the elastic region. For MECHENG 3A03, you want to be elastic region. Plastic region is another course I teach. It's 3CO3, which is in manufacturing. Okay, so for this course, we want everything in the elastic region. So what you can see over here is at this point, right? We will call it our yield strength. And this point over here is our ultimate strength. And over here, as usual, this is our failure. And then the gradient over here, this is our Young's modulus. By the way, I forgot to tell you, my bad. I will post all these written notes on Avenue to Learn. Okay, but if you want to copy at the same time, feel free to do so. Okay, so everything is made available. So you can see over here, experimental tests are required to find the relationship between stress and strain. So what is this experimental test that they do? Okay, so the experimental test is usually carried out in uni direction. Okay, so uni direction, what do I mean by uni? Uni means one. Okay, so uni direction means one. So uni, it can be in, okay, so this is our material. It can be in tension, or it can be in what? It can be in having other configuration. It can also have in compression, or it can, there's another configuration. Okay, and when you apply a torque, right, this can be in shear. So to relate this with the formula, so all this, so we know that stress is equal to force, or these are all P. Okay, P. So for both of them, stress, normal stress, is equal to force P divided by area. For this case, the shear stress is equal to TR over J, okay, which you have learned from 2PO4. So it's a torque multiplied by radius divided by the polar moment of area. You get your shear stress. So the experimental test is either carried in this configuration, or not N, or this configuration, or in this configuration. So it's either one. Okay, you don't do all three. Now if you now go back to our structure now, okay, so if we were to go back to our structure, So we go back to our structure now. I'm going to copy and I'm going to paste. All right. So if you look at our structure now, can anyone tell me which data to use? Are we going to use are we going to use, so you look at our structure now, right? Are we going to use a tensile material property? Okay. Are we tensile only? Okay, only. Or we going to do a compression only or shear only? Okay, I'm going to stop here for a bit and I'm going to, okay, you can answer my question, or if you have any question, you can ask now. Okay, so please do ask question. Okay, anyone, please. Thank you. No question with the content? It's awfully worrying now. Okay, then if that's the case, then can one of you answer me which material property you will choose? Okay, so the data handbook will carry out tests in tension only, compression only, or shear only. So which one will you use based on? Yep,
I think it would be tension only.
tension only. Anyone else?
I agree. I'd say tension only.
Okay. Hey guys, listen, I'm really so appreciative that you answer. Okay. It's really lonely down here, okay, which I don't see your face at all. It is so different, okay. If I lecture like that for the next 10 minutes, if you don't reply, I think I'll buy a gun, I'll shoot myself for crying out loud, okay. Right. So you guys will say tension only. But
How about shear only?
shear only. All right. So I like that. Okay. I like thinking people. Okay. Before we go on, I would like to train engineers that are thinkers. Okay. I don't want to train engineers that are following the world. Like for example, I'll give you a recent example. I don't understand why in this stage where we have coronavirus that everyone is just rushing to buy toilet paper. Does not make sense at all. Okay, okay, that's my point of view. Okay, we should not be worrying about toilet paper, should we? Right. So I want to train thinking engineers. Okay, I don't want to train. Yeah, I'm real passionate about this. Okay, now tension only. You're right. Shear. Uh, you can be right also, but we have to be able to link our structure. So our structure now, okay, have what? It's under. So the structure is loaded under both normal and shearing stresses. Okay, we are loaded. So the structure is loaded based on normal and shearing stresses. The problem of when we apply tension only, if we just use this data only, we will only get the normal stress only. And then if we do the torque, okay, or when we do the test in shearing, we only get shearing stress only. Okay, so but our structure is both loaded under both normal and shearing stress. Okay, it's a fact. Okay, you cannot isolate one and consider the other. Okay, we can't do that. So how do we go about selecting the right material property? So the principal stress calculated is based on both normal and shearing stress or shear stress magnitude. Sorry, and shearing stresses. It's not just a magnitude, it's a vector that we're interested in. That's why for this question that you see, right, we are